Hey everyone, and welcome back to our next lesson in our course of study in Regents Chemistry. Today's lesson is going to be on rounding and scientific notation and how exactly we do round numbers that are a result of different operations in chemistry. And we're going to start with addition and subtraction. Now, when we add and subtract numbers, the resulting number can only be as precise as the least precise of the measurements to be added or subtracted. I always find this interesting. If you think of trying to do longhand addition, you don't just come up with extra decimal places out of the blue. Sometimes you get this on a calculator. You might multiply, 3.1 times 0.7, and you get something crazy like 2.1436798. And it's like, well, where do all these decimal places come from? Calculator's just spitting out these numbers. Well, they don't really mean anything, and they don't really hold any significance. So when we add and subtract, depending on the precision of our numbers, our answer can only be as precise as the least precise of the numbers that we added or subtracted together. So we have to round the answer to the place of precision of the least precise measurement. Now in the example problems, the level of precision will be underlined. So round the following number to the nearest tenth. Well, we have a decimal, so our precision is farthest to the right. We want to round this to the nearest tenth. Now you have a place chart in your notes. The nearest tenth is one spot after the decimal, so we want to round to that number. So we look at the one to the right, that's a 3, and it tells us to keep it the same. So this becomes 23.3. Now this is just a quick review and rounding. You guys should be able to do this. This 23.337 would be a number that resulted from, let's say, someone adding or subtracting. To the nearest hundredth, we round, this becomes 23.34. The nearest 1, this becomes 23. And the nearest 10, look to the right, that 3 tells us to keep it. This becomes 20. So 4 different ways to round the same number. Now this is an example from start to finish of adding 3 different numbers together with different levels of precision. You can see here precision, and the first number is in the tenths, the second one in the hundredths, the third one in the thousandths. So when we add these together and we get an answer, what we want to do is round it to the least precise number, which in this case is this first number because it only goes to the tenths. We don't know in that number 33.5 what the value is of the digits coming after, all the way to the thousands. So just so you can kind of see this, I think it'll make a little more sense straightforward. And then we have 0.977. If this all lines up, we don't know what's here, here, and here. We can't just put numbers here. We don't know what that number is in the 33.5. So we decrease the precision of our other numbers and only round to the tenths place. So our number rounded to the tenths is the 3, and the 5 tells us to raise that 3 up to a 4, and we get 42.4 centimeters. Now the rule is slightly different for multiplication and division. Our answer, again, we're still going to deal with precision, but our answer can contain only as many sig figs as the measurement with the least number of sig figs. So whichever number that we multiplied or divided by that has the fewest number of sig figs, our answer has to match that amount. So we'll take the same number as we did before, 23.337, round to 4 sig figs. There's no zeros in here, so our number starting from the left would be these 4 digits. So this becomes 23.34. To 3 sig figs, 23.3. The 3 here tells us to keep it, so it's a 23.3. 2 sig figs would be the first 2 numbers. 3 telling us to stay. And again, the same thing here. We'd have to round to 1 significant figure. This would be 20. 20 is 1 significant figure. It's only the 2. The 0 does not count because there is no decimal place. If we add the decimal place here, now this becomes 2 significant figures. We don't want 2. We only want 1. So we want to make sure that we keep that decimal point out of there. On the other side here, our precision with no decimal place is the place here, which would be the 10,000th place, and round that to 6 sig figs. Well, we don't have any numbers here, and we only have one significant figure, as 10,000 is. But remember what we can do with the decimal. In 10,000, there is a decimal place there. We're not showing it in this number, but if we do, that one significant figure now becomes 5 significant figures. So just by adding that decimal, it's making those 4 zeros at the end significant. Now, if we want 6 sig figs, right now we have 5. We add a 0 at the end. The number is still the same. 10,000.0 is the same thing as 10,000. And that shows 6 significant figures. To do 5, all we'd have to do is just put the decimal at the end. To show 3, there's a couple ways we can do this. We want to show these first 3 numbers here, but how do we not count these other ones at the end here? They are a place value. They are counting up for our 10,000. They hold some type of value. So how do we show 3? Well, there's one way we can do it. We can put a line over the 0 that would be significant, and everything from there to the left would be significant. So this would be 3 sig figs. The other way we could do it is with scientific notation, which I'll show you in a minute here. And the way we would do that, we would take the significant digits that we want, in this case the 100, and we would do something like that, times 10 to the 4th. And for one significant figure, we can't just call this 1, because 1 is not the same thing as 10,000, but we can say 10,000, we can put a line over it. I guess as 10,000 is, it is one significant figure. So we don't necessarily need the line. But we could also use scientific notation. We'd only want to show that one significant figure. So we would say 1 times 10 to the 4th. Now that looks like the same number here, 1.00 times 10 to the 4th, or 1 times 10 to the 4th, but it's not. Because this initial number here, the 1, is different between those two. And we'll get to that in a second. So a little bit of practice with multiplying numbers. Now this rounding only occurs after you get your answer. Okay? So perform your operation with your calculator, show your work. And then when you want to go around, we look back at our numbers. Okay, this 9.22 has 3 significant figures, and the first one has 4. Well, we can only be as precise as our least precise measurement, so we can only show 3 sig figs in our answer, which is going to be the first 3 numbers here, 619. And we want to round this last place off. So 619, we look at the 5 to the left there, that tells us to raise it up, and it becomes 620. But make note, there's a decimal here, because that decimal makes the 0 at the end significant and gives us 3 significant figures. Otherwise, we're showing 2. Suppose you could also write this as 620 with the line over the 0. We could also write it using scientific notation, which we're going to use now. What is it exactly? You've probably seen numbers expressed in scientific notation. We're going to learn how to convert them into and out of scientific notation, so from standard notation into scientific, or from scientific into standard notation. And this notation is used to express really big and really small numbers as a power of 10. And it puts those really large and really small numbers into a usable form by compressing them, instead of having to write out something like 1 billion. That's a lot of zeros. I don't really want to write all those zeros. So we use scientific notation. It's much easier, less writing, cleaner to use, especially when using it in calculations. Now the key is that we take the significant figures from the number and put it into this form, where the endpoint n are the significant figures from the number. Okay? And we can change that amount, kind of how we did before. We can change the amount of zeros. So we had 1.00 here and just 1 here. It's still representing 10,000. But when we wanted to show 3 sig figs, we put all those sig figs in the number here. The X is going to represent how many places the decimal moves after that first significant figure back to the ones place. Okay? So it's how many spaces we move the decimal to make our scientific notation or to expand it. You always want to move the decimal back to the ones place. So we'll try a couple examples here, some with some large and some with some small numbers. The Earth is 4,600,000,000 years old. Okay, well, in this number, we have 2 significant figures, the 4 and the 6. And that's going to get added into the first part. Whoops. It's not exactly the straightest arrow. Into the first part of our notation, the 4.6. We then count. Okay, so from the ones place here, we want to make this number in between 0, greater than 0 and less than 10. Okay, so we move this decimal back to this spot here to make 4.6, and we count how many spots that was. And even though I've been doing this for a long time, I still got to count mine every time by writing them out. Okay, there's 9 places back to the ones place. All right, so this becomes 4.6 times 10 to the 9th. The 9 telling us how many spots we're moving. Now this number will get smaller if this exponent is negative. Okay, a positive exponent will make the number bigger. A negative exponent will make the number smaller. Next example, we have 3 significant figures, 3, 3, 4, and a whole lot of zeros after it. This number is significantly bigger than the age of the Earth. Now, from the first significant figure, the 3 here, all the way back to the ones, we count how many spaces that is, and that is 19 places. So our 3 significant figures become 3.33 or 3.34. And we always use this times 10, our base 10, to the 19th power, telling us that we move the decimal 19 spots. So decimal form. We have a number here. We'll do a couple of these examples. 4.73 times 10 to the 6. The first thing that we want to do is write out our first 3 significant digits, the 4, the 7, and the 3. And then there were 6 places from where our decimal place is, all the way back to the ones. So we just add in zeros as we do that. And if we write out our scientific notation into standard, we get 4,730,000. These next 3 examples are all representing the same amount, 20,000. We have different amounts of precision in each one. 2.00 is telling us we have 3 sig figs. So we have to show that in our expanded number by putting the line above that middle 0, meaning that the 0 with the line above it and everything to the left is significant and therefore included in our number. The one below it, since we only have 2 significant figures, the line is going to go above the first 0, meaning that the 2 and that first 0 are significant. So we're only showing 2 significant figures there. The bottom one here with no zeros only has 1 significant figure, and we want that to correlate with the number in our standard notation. So we have no decimal, no line, and this 20,000 only shows 1 significant figure. For the last one, 3.71 times 10 to the 8th. We have 3 significant figures, so we write those, and we move the decimal 8 spots back to the ones place, and we get a number. I always got to put my commas in here. 371 million, the amount of dollars in my bank account. Converting small numbers. So this is kind of the same idea as converting large numbers, except the amount of places that we move the decimal is going to become a negative exponent. Okay? An atom of carbon weighs a very small mass. Okay? Small enough where I don't really know what the suffix is for that amount of grams. It's too small, but I can tell it to you in scientific notation. Okay? Now, our significant figures with a decimal place are the ones all the way on the right. Any zeros in front of the leftmost integer do not count. If this is unclear, make sure you review your rules for significant figures. Okay? At this point, we count the number of spots back to the ones place. And the amount of spots that we move that becomes our exponent. And since we're moving it to the left, it's going to be negative. So negative exponents always indicate a number that is less than 1, whereas a positive exponent indicates a number that is greater than 1. Our distance between hydrogen atoms and a molecule of H2 gas is a really small number there. In scientific notation, it's 3.70 times 10 to the minus 8th. Notice the 0 at the end of the number here. That is significant because it's coming to the right of non-zero numbers with a decimal in the number. So we include all of those in our scientific notation number. The first integer is going to be 3, followed by the decimal point, and we count how many spots to bring it back to the ones place, which in this case would be 8. It's a number less than 1, and we move the decimal to the left, so we're going to have a negative 8 exponent. A couple examples here. 8 times 10 to the minus 3. We know we have one significant figure, so we write that. And then we move the decimal. I'll kind of show you here. We move the decimal 3 spots, and the negative tells us we're going left. So we're going to go 1, 2, 3, add in our zeros, and we get 0.008. Same idea for the next ones. We write out the significant digits first. 80, we had our decimal here, and it's going to go back 3 spots. 1, 2, 3. Okay, and we get 0.0080. And again, that 0 at the end is significant. We can keep putting zeros in the front here. It doesn't really matter. They're not significant. 8.00, same idea, but we're going to show that other 0 at the end is significant. So we start with writing our significant digits and move our decimal however many spots indicated in our exponent. We're going to do a fair amount of practice with this. If you guys have questions, make sure you write them down and ask them when you get the chance. Hope everyone has a wonderful day.